All right, let's talk about some more problems. So again, these problems are very long. I'm going to do a bunch just to give you more resources. You don't even have to watch this video at all, but if you do watch this video, just watch one problem and then work on some of the problems on your own and then come back later for another problem, okay? Don't have to watch them all back to back. All right, so we've got an island that is 2 miles north of its closest point along a straight shoreline. All right, so we got this nice shoreline. And then there's a beautiful island that is 2 miles north of the shoreline. A visitor staying at a cabin on the shore that is 6 miles to the west. A nice little cabin on the shore that is 6 miles to the west of the island. Okay. The visitor is planning to go from the cabin to the island, and they can run at 8 miles per hour. So, you know, if they were running, they could run 8 miles per hour over here. If they were swimming, they could swim 3 miles per hour. But we don't know where they're swimming, right? If they wanted to, they could swim directly from the cabin. Or they could run part of the way and then swim from there. Or they could run almost all the way there and swim perpendicularly. But we don't know how they're going to run and swim yet. But they do swim at 3 miles per hour. We'll write that down later. How far should the visitor run before swimming? Okay, so that's what it's asking, right? Do they swim here? Do they start swimming here? Do they start swimming here? Who knows? We're going to figure that out. So in general, let's just draw a little triangle. It's going to be a right triangle. And say that this is what we're trying to find. And you could call this X. And I have literally done this problem calling this X, but it's much messier. Because because this is the natural thing to call X, right? This is the decision. This is what we're trying to decide. How far are we running? So X is how far we're running, and then Y is how far we're swimming. And again, we can swim at 3 miles per hour. That's where we put that one. So let's start with this process because this is the natural way to formulate the problem. And then we're going to go back and maybe rename something. And that's okay. A lot of times in problems, you can't see the future. You can only see the future if you're a math professor and you've done this problem before. But I want to show like an authentic problem solving technique is that this is how it makes sense to formulate the problem. How far are we running? Let's call that X. How far are we swimming? Let's call that Y. And then see where we go from there. This is our first step. X is the distance run, Y is the distance swam. You could write that down, that'd be even better. And we're trying to minimize the time. Well, the time is just going to be the time running plus the time swimming, right? I don't know if I can barely fit that. And we're running at a constant speed. Or swimming at a constant speed, so we can use a formula that you may have seen before, that the distance is the rate times the time. We care about the time though, so let's divide both sides by r to get time is distance over rate. So we're trying to minimize the time, which is the distance running over the rate running, x over the rate, x over the rate of running is 8 miles an hour, plus the distance swimming divided by the rate swimming, y over 3. And this looks fine. And you might say, Jason, what's the problem with formulating the problem this way? This is a pretty nice equation, no problem. But let's do that step 4 in the step-by-step process. Okay, we're trying to minimize this variable. Let's write that constraint equation. Okay? So how that constraint equation, that step 4 says write an equation relating x's and y's. And it's kind of hard to do it right here. What we have to do instead is look at this triangle. The triangle is what actually tells us stuff about the problem. And in the triangle, there's not an x. The base of the triangle is 6 minus x. We're going to have to use Pythagorean theorem on this and FOIL it out, and it's going to be a binomial, and that's where things are going to be really messy. Right? If you did it this way, the next equation would be 6 minus x squared plus 2 squared equals y squared. And we'd have to solve for y, and it's just a little bit more complicated than it needs to be. It works. You can absolutely do it this way. But what I'm going to do is I'm going to switch these two things. Okay? Let's get rid of all these x's real quick and say, let's call this x. This over here is 6 minus x on the left now, because they have to add up to 6. And this is our final answer. This is what we're eventually going to be answering in the question. So let's remember that. X is not our answer. So now this is how far we're running. So we have to slightly change our objective function. This is the distance we're running now. So the objective function, this t function, is not much messier. But now our constraint equation relating x's and y's is going to get a lot easier. We know that x squared plus 2 squared equals y squared. Now this is much nicer because we don't have any linear terms. We don't have to FOIL anything out. And then what is our domain here? X, well, the smallest that x can get is 0, and the biggest x can get is 6 miles. Y, the smallest distance we could ever swim, is 2 miles, which is a long way to swim, or it must be like a triathlete or something. And the biggest we can swim, we'd have to use the Pythagorean theorem. I think you get 2 times the square root of 10. Turns out the y one won't really matter, but it's good practice. So we have most of the stuff already. Now we just need to use substitution to get our objective function to have only one variable. So you can solve for y or you can solve for x. It's up to you. I'm going to solve for y real quick because all that does is requires me to take the square root. And normally you need the plus or minus square root, but y is going to be positive, so we only need the plus. So our objective function t, we're replacing y. T is 6 minus x over 8 plus y, which is the square root of x squared plus 4 over 3. So still not easy to differentiate. And again, this is our interval for x. This is where we have to find the absolute extrema. As soon as you get here, it's just a 4.3 problem. Check the endpoints, find the critical points, pick the biggest or the smallest. We're trying to find the smallest time here. So before taking the derivative, let's rewrite this function a little bit to make it a little easier. T is a function of x. 6 minus x over 8, let's write that as 6 over 8 minus x over 8. And then that second thing, let's write that as 1/3 times x squared plus 4 to the 1/2. The 6 over 8 reduces to 3/4, but we're taking the derivative anyway, so it's gonna disappear. Let's take the derivative. T prime of x, the derivative of 6/8 is 0. And actually, that's the derivative of x over 8, that's the derivative of 1/8 x. It's going to be minus 1/8 here. And then we'll use the power rule, 1/6. Leave the inside the same, subtract a power, multiply by the derivative of the inside. We have to use the chain rule because the power rule only applies when the inside is x. The inside of those parentheses is anything other than x. We have to use the chain rule. And let's rewrite this a little bit as well. And then we'll use it to find the critical points. Negative 1/8 plus the 2 cancels with the 6 to be 1/3. You're going to get x over 3 times the square root of x squared plus 4. So critical points are when this is undefined. It's going to be undefined when that denominator equals 0. But x squared plus 4 is never going to equal 0. It's always positive. It's always at least 2. Well, x squared plus 4 is always at least 4. Okay, so the only critical points are when the derivative equals 0. And to solve this, we'll multiply both sides of the equation by the LCD. Or you could add 1/8 to both sides. I think so multiplying by the LCD is a really good strategy here, but I think a lot of people would just add 1/8 to both sides. So again, going to try to show things as I expect a lot of you to do them, but both are good. Because then we can cross multiply. We cross multiply, we'll get 8x equals 3 times the square root of x squared plus 4. How do you solve a radical equation? Get the radical by itself and square both sides. Divide both sides by 3. 8/3 x equals the square root of x squared plus 4. And now we can square both sides. 64/9 x squared equals x squared plus 4. It's a little messy, but not too bad. Let's subtract an x squared from both sides. That's 64/9 x squared minus 9/9 x squared equals 4. That's 55/9 x squared. Multiply by the reciprocal, take the square root of both sides. X squared is 4 times 9 over 55. That does not reduce. X is plus or minus the square root of 36 over 55. And again, we only want the positive value for x here. So it's going to be 6 over the square root of 55, which is about something. Six divided by the square root of 55. Holy moly, my phone is going crazy right now. About 0.8. Wait, this doesn't look good. Because our objective function, the thing we're trying to minimize, right, is 6/8. Let's write that as 3/4. Minus x over 8 plus 1/3 times x squared plus 4, the 1/2. Oh, all right, that is it. That is what we were expecting. All right, good use of the graph here. Yeah, so that's where our critical point is. It's about 0.809. So to find the absolute minimum, we have our 3 candidates. Candidates are at the endpoints, right, when x is 0 and when x is 6, and at the critical points when x is about 0.809. Let's find how long the times, again, these are the x's, not how far we're running, but how far we're not running, remember. And let's find the times for each of these. So plug them all into our original time function. So the time it takes, if x is 0, is 1.417 hours. The time it takes when x is 6 is 2.108. And the time it takes when x is 0.809 is 1.368. Which of these is the smallest? Hopefully it's at the critical point, or we did a lot of work for nothing. All right. It is indeed at the critical point. So the time is minimized when x is 0.809. But remember, we don't actually care about x. The reason why we called x this is it made the problem much easier. If you don't believe me, try it. Try it with x being the other one. Yeah, we really care about 6 minus x. 6 minus x is how far we're running. So what's 6 minus 0.809? I don't want to do that in my head. 5.191. So this is how far we need to run. And again, I just want to just kind of combine what's going on here. Just look at this part again. When x is 0, the time it takes is 1.4 hours. When x is 0, what does that mean? That's when this is equal to 0. That means, so if we just run directly, like as far as we can, so that we're perpendicular to the island, if we run all the way, it's going to take about 1.4 hours. The second one is when x is 6. That means we're swimming all the way. We're swimming all the way. That's swimming like over 6 miles. We're swimming over 6 miles. It's going to take us over 2 hours. And if we're running about 5.2 miles and then swimming a little diagonally, that's optimal. That's going to take us also about 1.4 hours, but less. All right. And it didn't ask about the time here, but if it did, you could convert it to hours and minutes. And that's what we wanted to do here. That's a 16-minute video on the first problem. I have 2 more problems in this video, but again, go ahead and pause, take a break, do some more problems, and then come back. Or you can start working on these. That would actually be a really good strategy. Start working on these and then watch the rest of the video. All right. Example 4, owners of a car rental company have determined that if they charge customers P dollars per day to rent a car, where P is some price between $50 and $200, the number of cars N they rent per day can be modeled with a linear function. N is a function of P, and N of P is 1,000 minus 5P. Okay, so this makes sense. The bigger the price, the fewer people are going to be renting these cars. And furthermore, if they do charge less than $50, and again, if they're in this range of $50 to $200, this is the formula that shows how many cars they rent. But if they're outside of that range, they will rent all of their cars, all 1,000 of them. If they charge $200 per day or more, so again, if we're outside that range on the other side, they will not rent any cars. Assuming the owners plan to charge customers between $50 per day and $200 per day, so we can assume that we're in that part of the domain, how much should they charge to maximize their revenue? There's no picture to draw here, so we're going to kind of skip that part, but we have some variables. Right? The variables are N and P, which we already did. We charge P dollars to rent N cars. That's what we're doing for step 1, identifying our variables. And now what do we want to maximize or minimize? We want to maximize the revenue. And again, we know our domain is 50 to 200. Next up, what is our revenue function? It doesn't tell us. But, you know, for selling things, anytime we're selling things, the revenue is just what are we charging? How many are we selling? Multiply them together. So, no problem. We know the revenue. Revenue is how many cars are we renting? How much are we charging? Multiply them together. Great. That was step 3. Step 4 is finding an equation that relates our independent variables. Find an equation that relates N and P. I found it. N equals 1,000 minus 5P. You can either write it with function notation or just as the variable itself. These are identical, the things in parentheses, the things in circles that I just erased. And then we're going to substitute out that N. So revenue is now a function of a single variable. N is 1,000 minus 5P, so we replace it, times P. And our revenue function is, again, a function of a single variable. We're writing it in function notation, the nice quadratic function like so. And again, we're trying to maximize this. On the interval, P goes from 50 to 200. Once we get here, it's exactly a 4.3 problem. Find the global extrema, the absolute extrema. Those words mean the same thing. Specifically, want the maximum. So we're going to check the endpoints. We're going to check the critical points. So we're going to check 50, comma something, 200, comma something, and the critical point, which is r prime of p, is 1,000 minus 10p. This is defined everywhere, so we don't have to worry about when it's undefined. Set it equal to 0. We'll go through this a bit quickly. 10p is 1,000, or p is 100. $100 per day for these rental cars. That is our critical point. Again, these are all the prices, our independent variable for this function, and the output is the function value, which is our revenue. We want to find the biggest revenue. We know from the extreme value theorem that we have a continuous function on a closed and bounded interval. So we just pick the biggest. All right, so plug these revenues into a calculator. The revenue as a function, we'll call it x here because it makes Desmos happier, is 1000x minus 5x squared. All right, and we are curious, well, what is the revenue? Wait a minute. Yeah, what is the revenue when we charge $50 for a rental car? If we charge $50 a day for a rental car, we rent all of our cars every day and make $37,500. If we charge $200 a day, nobody's buying. Nobody's renting our cars if we charge $200 a day. Charge $50 a day, we rent all of them. We charge $200 a day, literally none of them get rented. So if none of them get rented, our revenue is a fat 0. That's not going to be our maximum. That's not the play. 100 is our critical point, just $50,000. Okay, there we go. That's what we want to do. What's the question asking? How much should they charge to maximize their revenue? They should charge $100 per day. For a rental car. That would give them a revenue of $50,000 every day. All right, here we go. Well, that problem was a little better than the last one. A rectangle is to be inscribed in the ellipse. Okay. Let's say we have an ellipse. Remember, inscribed means this. This is our situation. We're drawing our picture. That's the equation of our ellipse. What should the dimensions of the rectangle be to maximize its area? So you want to be a little careful here for using x's and y's, because the x's and y's mean something different than the x's and y's in the equation. So I'm going to call it A and B. These are the dimensions that we're looking for. Again, one of the quickest ways to figure out what your variable should be, with some notable exceptions, like I talked about in the first example of this video, example 3. One of the best ways to figure out what your variable should be is just look at what is the problem asking about. That's either going to be an independent variable or a dependent variable. So once the dimensions, those are the unknowns. We can name those. Let's name those A and B. And we want to maximize the area. Okay. I don't know where this problem's going, but we're just going to do the step-by-step problem, step-by-step method, and we'll see where it goes. I'm going to, again, another opportunity for me to show you guys problem-solving strategies. Okay. Sometimes for like really complicated math, I do look at the problems in advance, but this stuff, nah. We'll experience it together. It gives a more authentic approach, I think. So what do we want to do? We want to maximize the area. And it might help a little bit to graph the ellipse and become a little bit more familiar with equations. I think a lot of people are fairly comfortable with the equation of a circle, but less comfortable with the equation of ellipse. Ellipses all have this form: x squared divided by something squared plus y squared divided by something else squared. And that has to do with the length and the width of the ellipse. And we set them equal to 1. And then you can do horizontal and vertical transformations as well by subtracting things on the inside. But let's say that you didn't know that and you wanted to get a visualization of this ellipse. That would be a very good idea to start. So again, I said x squared over something squared. That something squared is how far to the side we go. So that 4 is going to be double the square root of the... Sorry, that's confusing. So it goes out to 2 because 2 squared is 4. Then the top is 1. All right, so the biggest the rectangle can be, because of course we don't know the dimensions. Maybe it's inscribed like that, or maybe it's inscribed like this, right? Depending on what the height is, we can go further along the edges. And in fact, if we had a really, really thin rectangle, right, we could go have this almost be a length of 4, right? It goes, the ellipse goes to +2 and -2. To maximize the area, oh, the area formula is easy here. Maximize the area, that's just length times width. And we know that A, the smallest A can be is 0, and the biggest A can be is 4, right? From -2 to +2 is a length of 4. And similarly, B is the vertical distance. If we drew a rectangle like this, B can be just about 1, or sorry, just about 2. All right, this is what we want to maximize. Now our constraint, that's something a little bit weirder, because you might just think, oh, let's just use this as our constraint equation. We have to make sure that that makes sense, or maybe we have to adjust this a little bit. Okay, A and B are not necessarily the same things as X and Y. All right, so what we have here, let's look at the points of this rectangle. The points where this rectangle intersects with the ellipse. And all of these points are, of course, going to lie on the equation. And again, we do have a coordinate plane here. All right, we do have this. We know this is the point 2, 0. This is the point up here, 0, 1, and it's symmetric. All right, so we're going to use information about these points to find information about A and B. So specifically, this top right point, since it's symmetric, this top right blue point, we know an equation for that. That's the equation A over 2, or sorry, the ordered pair A over 2, comma B over 2. Right? If A is the whole length of the rectangle, then half of that is the X coordinate, because it is symmetric here. All right. So any coordinate, any one of these points, and again, similarly, like this point down here would be A over 2, negative B over 2. This would be negative A over 2, B over 2, and so on, right? So we do know all the points on this rectangle. So can kind of put that. So the point A over 2, B over 2 has to be on the ellipse. So we're not actually just replacing the X's and the Y's. The X coordinate is the A over 2. Okay. And it doesn't matter which one we pick because they're all getting squared. So the positives and the negatives don't matter because they just go away when they get squared. So our constraint equation is going to be X, and our X coordinate is A over 2 squared over 4 plus Y, which is again B over 2 squared equals 1. Okay. Because those are points, the relationship between the ellipse and these lengths and distances. And this is kind of similar to example 3 in a sense that it could have been easier to find these x's and these y's instead of finding the a's and b's directly, but I don't think it is worth going back because I think it's pretty close in how easy they are. So let's just simplify this some more, and then we can substitute it out and get our nice optimization equation. So a over 2 squared, that's a squared over 4. That's all over 4. This becomes b squared over 4. Now there's a couple of ways you can do this, but one way that you can simplify this is just to multiply both sides of the equation by 4. That gives us a squared over 4 plus b squared, when we distribute, equals 4. And we're trying to solve for one of these variables. It doesn't really matter which one we solve for. If we solve for b squared, we can just subtract over the a squared over 4. I really don't like fractions. Let's multiply everything by 4 again. We multiply everything by 4 again, we get a squared plus 4b squared equals 16. And now at this point, for me anyway, it's easier to solve for a squared. It doesn't matter which one you solve for. So a is plus or minus the square root of 16 minus 4b squared. But we don't need the minus because a is a length here. They're gonna give us the same answer. Substitute that into our area function, and now we have a function of a single variable. Writing a of b is the same as writing f of x. You could also just write a without the b here if that's extra confusing. Is a, which is the square root of 16 minus 4b squared, times b, which is just b. And we're maximizing this on the interval 0 to 2. Notice that we're not doing the interval 0 to 4 here because our variable is just b. So we need to look at the constraints for b. All right, this will be a little bit messy, but now again, after this point, it's now a 4.3 problem. So we have to consider what is the area on the endpoints. It's going to be 0, right? When the b is 0, it's going to be an infinitely thin rectangle. And when b is 2, it's going to be an infinitely thin rectangle this way. You could also plug in 0 and 2 and get that, yes, these are not very good candidates to maximize the area. We need a critical point. So let's rewrite this function. A of b is 16 minus 4b squared to the 1/2 times b. We're going to have to take the derivative, which is going to use the product rule. So a prime of b, well, that's going to be the derivative. Oops, I wanted to do that in a different color. So I will. This can be our f. And this can be our g. Green and red are really terrible choices. I'm using Microsoft Edge instead of my open board app to have things be more similar to how you guys would be looking at it. So the derivative of the first thing times the second. The derivative of the first thing requires the power rule, leave the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside, negative 8b. That is just f prime. F prime times g plus f times g prime. The derivative of b with respect to b is just 1. So let's rewrite this and find the critical points. That's going to be a prime of b equals, well, let's simplify this a little bit, right? We're going to have negative 8. That becomes a 4 when it's divided by 2. We have a b squared on the top, 4b squared on the top. And on the bottom, we have the square root of 16 minus 4b squared. Do a double check, make sure we got everything taken care of in that first term. We didn't. We are missing a negative. Good. That's why we check. Plus the other one, which is just the square root of 16 minus 4b squared. Critical points are going to be when this is equal to 0 and when this is undefined. So it's undefined. Let's go off to the side maybe. It's undefined when the denominator equals 0. That's when 16 is 4b squared. When 4 is b squared, when b is equal to 2, plus or minus 2. We've already incorporated that. Negative 2 is not in our domain. Positive 2 is one of our endpoints. We've already taken care of this. We don't need to consider this again. We don't need to add this to our list of candidates at the top. It's probably not going to fit here. It might be a messy number. So we have to find next when it's equal to 0. So set it equal to 0 and solve this equation. Whenever there's fractions, the best way to solve the equation is to multiply both sides of the equation by the LCD. And then we might have square roots that we have to worry about afterwards. Multiply the left, it's still going to be 0. LCD here is the square root of 16 minus 4b squared. And again, we're doing it to both sides. Here, I'll put the parenthesis here. Kind of an abuse of the notation, but works out. Left-hand side still 0. Distribute it on the right-hand side. The first term, the square roots cancel. We get negative 4b squared. And the second term, it's a square root times the square root. So it just becomes 16 minus 4b squared. We'd have a real problem if these b squareds canceled, but luckily they don't. We have 0 equals negative 8b squared plus 16, or 8b squared equals 16. B squared equals 2. B is plus or minus the square root of 2. We only care about the plus. That is the location of our other critical point. So what's our area when B is a square root of 2? Well, let's write our area formula. Let's use x so Desmos is happy. Area as a function of x is 16 minus 4x squared to the 1/2 times x. This is our area function. And again, we're curious about this area function only from 0 to 2. Trying to maximize the area should be at the square root of 2. And that's exactly what the square root of 2 is. 1.414 about. What is the area when x is the square root of 2? Area of the rectangle is 4. So these are our 3 candidates. Which of these has the biggest area? This is our b value. This is our area. When b is square root of 2, we get the biggest area here. Okay. What should the dimension, let's remember the original problem. What should the dimensions be? What's the maximum area? All right. Dimensions should be A what is A? We don't know. Something by the square root of 2. What's the relationship between A and B? Here we have it. A is the square root of 16. A is the square root of 16 minus 4b squared. B squared is 2. 16 minus 8. The square root of 8. That's 2 root 2. So 2 root 2 by the square root of 2. For a maximum area of their product. Multiply those together, you get 2 times the square root of 4. That's 2 times 2. That's 4 units squared. Technically, these should have the word units in them as well. And that's our answer. So to kind of give a little picture of what this looks like, let's look back at our ellipse. What's the rectangle that maximizes these? Well, it's going to have the vertical line of y equals 1/2 of that vertical distance, which is the square root of 2. That's where the vertical line is. And it goes from negative 1/2 square root of 2 up to positive 1/2 square root of 2 times 2. It's that on the top. It's the negative on the bottom. And then we have to do something very similar. X is going to be equal to, let's get those vertical lines. X is equal, what is the X coordinate? The X coordinate is half of the A value is where this X coordinate is. Half of the A value is just the square root of 2. And again, that's going to be going from Y is negative 1/2 square root of 2 up to positive 1/2 square root of 2. There's a cool little visualization. And there's also the negative version of this as well. Let me know if you have questions on how I constructed this box. It's kind of cool. You may have done something like this in a pre-calculus class, but I'm going through it pretty quickly. So this is the box. This is what we found the box to be, the dimensions of the box. And we're graphing those dimensions using some tricks of piecewise functions. And that's, I mean, if you just visually look at it, it should kind of make sense that yes, this box does kind of look like the biggest box that could be possible. Inscribed in this ellipse. And that's the end of the problem. And we have our answer. I just want to have a little fun now. So you can stop the video. That's the end of the problem. But if you want to have a little fun and see this problem a little bit more visually, I want to play with this a little bit. So we can do this for any B, actually. This rectangle for any B. I think what we're going to do is actually kind of complicated, actually. I think we just replace this with B. And then X is going to always be just like 1/2 times the square root of 16 minus 4B squared. I think. Let me see if that piece is right for any rectangle. Yeah. Good. So we have that for the first rectangle, and then the negative of that for the second rectangle. And then you kind of flip it for the X coordinates. So you just flip the domain in the range. So this becomes this is actually going to be kind of cool. This becomes the X equals that on the domain of this. I wasn't actually sure if this was going to work. I thought it was going to work, so I'm pretty excited that it is turning out to work. So that's going to be the left side. Wait, why is it not showing up actually? Did I jinx it? Oh, this should say Y. No, this should say X. The other one should say X2. Wait, hold on. No, it should say Y over here. There it is. Look at that. So we can actually visualize using this formulation, a clever formulation like this. We can actually visualize what the box looks like for any value of B. So if B gets smaller, as B gets closer and closer to 0, here, and I can type this in manually, right? 0.1, it gets really small. 0.01, the area is approaching 0 because B is that vertical distance. But as B is getting bigger, right? As B is getting bigger, oops, 0.2, 0.3, 0.4, Now the A value is getting smaller, like the width of this box is getting smaller. And so we're just trying to find how do we maximize that area. I hold on, it doesn't look right anymore. I think it might be a rounding error. I think it might be a rounding error. Either that or I made a small error. It worked on the other half, but you can get the idea. I don't want to spend a lot of time troubleshooting this, but that's kind of what happens. I really do think it might be a rounding error. No, it's like getting to like an asymptote, which is interesting. I wonder if it is a rounding error or if it is something else. Yeah, it's approaching the wrong thing. Yeah, it's probably just a small error that I made. I should go up to 1. Instead, it's going up to about 0.7. Interesting. Oh well, I'll work on this. I think I'm off by like a square root of 2 factor here on these y coordinates. Do I fix it? I think I can really just do it like this. Yeah. That's what the function should have actually been. That actually goes up to the right amount. All right. Fun time. And then, of course, I would have to change the other one. No, that's not right either. I don't know. It's going to take too much time, but it's fun things that you can do. Give you a visualization anyway. Bye-bye. Have a good one.